Question 5 from the 2023 Advanced Higher Physics Examination from the SQA. When discussing general relativity, the American physicist John Wheeler stated space-time tells matter how to move and matter tells space-time how to curve. Now for 3 marks you have to use your knowledge of physics to comment on a statement. Now rather than go through the old palaver of the bed sheet or the rubber mat stretched out and the big heavy mass pulling it down, we'll take a different tact here. But before we do that, let's introduce ourselves to John Wheeler. And that's the man himself. John Wheeler was an amazing physicist, worked with some great physicists throughout his life, died in 2008 in New Jersey in America, and one of the top physicists of his time, and he's attributed to that comment. So let's delve into how we attack these 3 marks and put down as much sense as we can. Well, first of all, I would put down something like this then. Einstein's general relativity theory gave a new explanation for the force of gravity. We are quite used to gravity as a force, a non-contact force, and we still can't explain why it's there, but Einstein's general relativity theory gave us a new way to understand gravity. I would put down something like this then. Einstein formulated a theory in which space and time are not separate flat dimensions, but in fact they're a 4-dimensional thing, the one thing, space-time connected. And this space-time fabric, if you can think of it that way, it can be warped by the presence of mass or energy indeed. Or more precise, it's the geometry of 4D space-time that is curved by the presence of matter or energy. Now, to back up his statement, we can, rather than do away with the talk about the rubber sheet and all that stuff, we can look at another alternative approach which shows your physics knowledge, and it's to do with going from 2 dimensions to 1 dimension, 2 dimensions to 3 dimensions. Now we imagine we've got 2 ants on a flat sheet of paper, and these ants live in flatland, the sheet of paper, and they don't know there's a 3rd dimension, so they just move up, down, across, to the left and to the right. Now these 2 ants set off in parallel tracks at the same speed, and there you go. According to them, they go about their business and one ant doesn't interfere with the other ant. But if we take that flat sheet of paper and we wrap it round a ball, then what happens is we change the geometry of the sheet of paper. We take it from a situation where we've got just simply 2 dimensions and we change it into 3 dimensions. Now remember, the ant doesn't know that it's in 3 dimensions now, it just lives in flatland 2 dimensions. But here's the big point. If the ants start off again in their track heading north, then what happens is as they head around the new geometry, they seem to be coming closer together. Now that would appear that the ants are being forced together. But what's forced them together? The ants would conclude or deduce that it's gravity. It's a new force called gravity. So by going from 2 dimension to 3 dimension geometry, we have introduced this kind of situation where the geometry throws up a new kind of force, a non-contact force. Now the flat sheet of paper's 2D geometry is now wrapped, as we said, into 3D. The ants don't know about the extra dimension. They walk straight and something brings them together. The ants would then deduce that there is a non-contact force pulling them together, just as we said. Now the paths that the ants follow in the 3-dimensional sphere, the paper wrapped round the ball, are called geodesics. And this is the shortest distance, the paths are the shortest distance between 2 points in curved space. So these ants are going the shortest distance possible, straight line, but in the curved 3-dimensional space, they're actually following a curve. So back to our physics again then. So matter and energy indeed curve space-time, and they really curve the space-time geometry. That's what we're thinking about, because space and time are just part of this 4D entity, and its geometry is distorted or curved by the presence of mass or energy. Objects, even light beams, would travel in space-time in the most efficient trajectory along the geodesic paths. And we can think of that if we bring in the story about the aircraft which always fly off from one part of Europe to the other part of Europe. They don't fly in a straight line, but they fly in a curve, and it's the curve which is the straightest line, believe it or not. So a curve on the 3D Earth is actually the straightest or the shortest distance, and it's the same thing that's happening in the 4D dimensional space-time when it's warped by mass. So here comes the important part here then. Gravity is a result of the curvature of space-time. That's what came up from the curvature of space-time. It can explain gravity, it can explain why things are pulled together, because they're maybe on different trajectories, but they'll be following curves in the space-time environment, the 4D space-time environment. Now, how can we prove that? You could add this for your extra information. You could say that it's well seen in the universe, any picture of the universe of different galaxies, and we see a situation called gravitational lensing. We see the image of the galaxy surrounding the actual galaxy. This is because what we get is the light beam is bent by the space-time distortion. It follows the curve of space-time, and we see it in fact as this image of galaxy round and not round the galaxy. The other point we can prove that the space-time is in fact telling particles or objects where to go is in Mercury's peculiar orbit. You can look that one up as well. So these are the things you can add to your general discussion. But if you do comment on what we've done there now, I am sure you'll get more than 3 marks, because it's a different tact and you're using your physics to describe that. So look it up on the internet. There's plenty of YouTube videos which you'll be watching which describe what happens when we have 4-dimensional space-time. It's very complicated. The geometry of it is very, very complicated, and the upshot of it all is that when matter is in space-time, it curves it, and it's this curved geometry that objects follow in their trajectories. So John Wheeler succinctly described it quite well. Space-time tells matter how to move, and matter tells space-time how to curve.